Hello and welcome to a video. This is a video for a couple of questions Faiza has just sent me. They look like quite fun mechanics questions, so I thought I'd quickly go through them. Okay, so standard ladder problem here. Let's start drawing a diagram. At least we know if we've got the answer right because they've told us what the answer is. So I'm going to draw that down there. Always draw the diagram again, even if it's drawn out for you, because otherwise the diagram tends to get a bit busy. Okay, let's see if we can figure out what's going on. Okay. It's got length 2A, weight W. Is it a uniform? Yeah. Okay. So it's right in the middle of A, and it's got weight W. Worth getting that done first. A and A. Okay, cool. What else have we got here? Oh, that angle's theta. So that angle's theta. Cool. What else do we know? Okay, it's an equilibrium. Rough ground, smooth wall. Yeah, so no friction here, but there will be friction here. And as there's nothing, well, I hope I haven't got anything pushing it towards the wall, in which case friction could go in the other direction. But almost every time friction goes in that direction. I'm going to put it at a maximum. I'm guessing it's at a maximum. And it will be a maximum if it's on a point of slipping. Yeah, the ladder is on the point of slipping. That's good. Good. Is there no other weight on the ladder? I don't think so. So let's do it. Okay, right, so that's what we've got basically. Let's put some more forces on here though. We're going to have a reaction here. We're going to have a different reaction here, and let's distinguish them by calling this RB and RA, because I'm guessing that's A and that's B. That's normally the case of the way these diagrams are labelled. Yeah. Okay, so I think we're good to go now. Okay, so how do we solve these problems? Well, lefts equal rights, which means RB must be equal to F max. Ups equal downs, which means that W must equal RA. That's all four forces dealt with. And then you've got to take moments at A. Every single one of these questions, that's what you do. Okay, we're going to have, if we're taking moments at A, that kind of wipes out the RA and the F max. And we'll have A times by W cos theta. Well, that should equal 2A times by, okay, let's do this carefully. You need the perpendicular component of the force times by the distance, so 2A times by, now what's that side going to be if there's your right angle? Well, as that's theta, Z angles tells me that's theta, which means that must be theta. Yeah? Okay, then I can see it's RB sine theta. Cool. Okay, so the A's cancel here, and we're left with W cos theta equals 2RB sine theta. Okay, well, let's get a tan theta involved, because I guess tan theta is involved in the answer. So let's just divide both sides by cos, and we'll have 2RB tan theta. Yeah? Now, okay, I don't really want W kicking around, because this is about mu. And F max, remember, is mu RA. Yeah? Because that's what connects the mu and the mu and the RA here to the F max. Okay, so what are we going to do now? I reckon we should try and use this and get everything in terms of the same thing. So F max is RB. And now I can also say, well, RA is W. But W is, I've got a double equal sign there, I'm not too sure about why that is. W is 2RB tan theta. So now I've got it all in terms of RB, if you see what I mean. So RB equals mu times by, that's a W by the way, it's just a very dodgily drawn W. Let me just make that a bit clearer. So this is going to be 2RB tan theta. And lo and behold, when you divide by that, you're going to get 1 over 2 tan theta is mu, and it's done. Okay, if the ladder were not modelled as uniform, state how this would affect the calculated value of mu, explaining your answer carefully. Well, if it's not uniform, yeah, let's find the exact line where things would have changed. If it's not uniform, that would have changed, yeah. None of the rest would have changed, would it? But if it's not uniform, that would have changed. And that's just because it wouldn't be right in the middle of the ladder. Yeah. Now let's say it was like 0.5a and 2a here, because it could have been closer to this. So I would point out like this, because they're giving you 2 marks for this. So it's no use to say, oh well, mu would change or something like that. You've got to say what direction it's changing in. So you can say something like this: if the ladder was not uniform, and the centre of mass was closer to A, because let's say how it changes as the centre of mass is closer to A, then what you're going to get is not W equals 2RB sine theta, but W will, let's think about it like this. If this was 0.5a and 2a, so I'm just making it go closer to that, then suddenly this would be W equals 4RB tan theta, which would make that a 4, which would make that a 4. Yeah, do you see what I mean? So I'm just working this through in my head, coming up with a completely arbitrary number of move this, twice as close here, so make that a 0.5a. And then all of a sudden, you can see that mu is decreasing. Yeah, the mu would decrease. Now, does that make intuitive sense? Well, I think, yeah, it does, because the weight of the ladder is closer to the bottom, which is surely going to make the ladder like less prone to slipping. I don't know, it's hard to see actually. It is hard to kind of like consider. I suppose it's possibly easier to think, well, W is related to RA, and RA, yeah, so yeah, if we yeah, I mean, but then again, W is just equal to RA, so that distance, it's all about this moments calculation, it really is. If this force is stronger, I guess it's also because the wall is smooth. By the way, I've said enough now to get both marks, I'm sure of it. But do let me know, actually. Let me know in the answers what it says here, because I'm often not brilliant on these wordy bits at the end. But yeah, if the ladder was not uniform and the centre of mass is closer to A, then mu would decrease. I'm pretty certain that that is absolutely true, because I've actually just run the numbers through with it. And if you increase the denominator, then the value of the mu is going to, sorry, no, we've increased the denominator, so the value of mu is going to decrease, yeah. But yeah, intuitively speaking, I think it's harder to see. As you move the centre of mass closer to the bottom, I don't know, it almost feels like mu needs to increase there to me. But I guess what that means is your moments, well, because it's already on the point of slipping, that suggests that you need a lower value of mu, doesn't it? Yeah, yeah, no, that makes sense. Okay, so that was that one. Okay, next one. What are we doing here? A particle me moves under the action of a single force. Now, when I just glanced at this, when I was copying it down, the thing which struck me was this force F is not constant. Yeah, and I'm always asking, is the acceleration constant in these questions? Because if it's constant acceleration, it's SUVAT. If it's not constant acceleration, it's variable acceleration, so you need calculus, yeah? And I want to know what technique I'm going to use. And I think it's going to be calculus, just because they ask you to find the magnitude of F when t is 2, which suggests that F is changing according to the time. You can also see it because this is displacement really, isn't it? Differentiate, you get velocity. Differentiate again, you get acceleration. But we're still going to have a t in there when we differentiate twice, because we're going to get 3t squared and then eventually 6t, which suggests to me acceleration is dependent upon time, i.e. acceleration is varying. So this is going to be a calculus problem, yeah? Okay, let's make a start on it. First thing we're told is at time t seconds, p is moving in direction of that vector. Yeah. Now, whenever it tells you the direction it's moving in, that's about the velocity. Velocity tells you what direction it's moving in. So let's differentiate it. Now, straight away, I would see this as t cubed minus 5t and 5t squared plus 6t. Yeah. And so my velocity vector is just going to be that differentiated, which is 3t squared minus 5 and 10t plus 6. Okay, now it's not good enough to say this equals I plus 2j. You must in fact say, well, if the direction is the same, then it's parallel to this vector, i.e. it equals a constant times by that vector. And that's what students are very hesitant to do, introduce a constant. Yeah? That way it would definitely be parallel to that vector. Okay, so what I'm going to do now is I'm going to say 3t squared minus 5 equals k, but 10t plus 6 equals 2k, so it's going to become a quadratic. If I just plug in now this into there, I'm going to get 10t plus 6 equals 2 times 3t squared minus 5. I've got the old quadratic, so I'm going to get 6t squared minus 10t, and then I'm going to get minus 10 at the end, but I'm going to be taking away 6, so I'm going to get minus 16. And so if I divide that all by 2, I get 3t squared minus 5t minus 8. Let's factorise it. 3t and t. Normally these factorise. What have we got here? Minus, let's have a minus 8 here and plus 1 here. I think that works, doesn't it? Minus 8t plus 3t is minus 5t. Yeah, cool. And so t is 8 over 3. So capital T is 8/3, yeah? Now you can always check these kinds of things and say, well, when I plug in my value of t, do I genuinely get, you know, a velocity vector moving in a direction of 1, 2, yeah? So let's quickly check. V equals, okay, 8 over 3 squared is 64 over 9, times 3 is 64 over 3, and then take away 5, well, let's take away 15 over 3, and then 8 over 3 times 10 is 80 over 3, and then plus 6, well, that's plus 18 over 3. What does that come to? 64, 54, 49 over 3. And then 80, 98 over 3. Now, have you noticed that the y component there is double the x component? You know, in other words, the j component, sorry, is double, you know, I plus 2j. Is that in the direction of 1, 2? Yes, it is, yeah? And that's just because that one is double that one, yeah? So it's definitely in the same direction. It's a scalar multiple of this. You just need to multiply this by 49 over 3, yeah? So there we go. We got it right. Okay, find the magnitude of f when t equals 2. Well, f equals ma. And so what I'm going to do for part B is I'm going to differentiate the velocity again to find the acceleration. I'm going to get 6t and then 10. And now I want the magnitude of f when t equals 2. So I'm just going to get a equals 1210 there. And therefore f equals 0.5 times by 1210, which is of course 6.5. So the magnitude of f is just going to be, quick use of Pythagoras, 36 plus 25, which is root, what is that, 36, 46, 56, 61 newtons. Do check that on the mark schemes though, but I think that should be right. And yeah, thanks for listening. Bye-bye.